Let's recap the Wilcoxon RankSum test for comparing the medians of two populations. So we're talking about non-parametric techniques, and now we're talking about comparing one population with another. And here we want to know, or we want to answer this hypothesis, or set of hypotheses, that the distribution of population 1 and the distribution of population 2 are the same. Okay, the shape, or not the shape, but the location of D1 is roughly the same as the location of D2. Otherwise, D1 is to the left or right of D2. Okay, this would be the two-tail test version. Okay, either D1 and D2 are the same, they have the same essential central tendency, or D1 is to the left or to the right of D2. They're not the same. Okay, that's another way of saying D1 and D2 are not the same. And how could they not be the same? D1 is either to the left or to the right. Okay, or we could be talking about an alternative hypothesis, which is D1 is strictly to the left of D2, okay, strictly on one side of D2, or D1 is strictly to the right of D2. Okay, so these are one-tail tests. This is a two-tail test. And so what would our test statistic here be, or what's the approach for addressing these kind of hypotheses? Again, this is kind of like saying the mean is to the left or to the right. The mean of population 1 is to the left or to the right of population 2. Okay? Or the median is to the left or to the right of population 2. But our particular test statistic, the approach that we're using, doesn't allow us to specify mean or median or something like that, just that the distribution is on one side or the other. Okay? So how do we approach this idea? Well, first we have y sub I observations. Okay, so we would have for population 1 and population 2, okay, we have a series of observations. Okay, so we have y1, y2, y3, y sub n1. Okay, so we have n sub 1 observations from population 1. Let's call this x. x1 all the way down to x sub n2. Okay, so we have n1 observations from population 1, n2 populations from population 2. Okay, and what we do is we retain this knowledge of which observations come from which population, but we mix them up and rank them from smallest to largest. Okay, so we mix all of these up and rank them from smallest to largest, but retaining the knowledge of which population they came from. Okay, so we rank these from rank 1, the smallest, to rank n1 plus n2. Okay, that's our total sample size from both populations combined. We have n1 from population 1, n2 from population 2, so the largest value is going to have rank n1 plus n2. And then everything in between. Okay, if we have ties, then we take the average of the observations that are tied, the average rank of the observations that are tied. Okay, and then we parse them back out into their two populations. So we have a set of ranks for these observations and a set of overall ranks from these observations. Okay, and then we sum the ranks for each population. Okay, you would imagine that if this distribution was roughly the same as this distribution, then their sum of ranks would be roughly the same. Okay, because you would have several lower observations here, several high observations here, and so on. Okay, you would imagine that the sum of the ranks for each population would be roughly the same if the distributions are the same. If you see that the sum of ranks for one population is really high relative to the other, then perhaps in this case, if this if this sum of ranks is high, for example, and this sum of ranks is low, okay, that would suggest that the central tendency of this population is to the right of this population, okay, because we have a lot of low ranks down here. We have a lot of small observations in D1 relative to D2, okay? So we might conclude that D1 is to the left of D2, okay, if the sum of ranks is really high for D2, or for population 2, okay? And vice versa. So if we had a lot of high-ranking observations here, a lot of low-ranking observations here, then we might draw this conclusion, okay? Or this conclusion. So that's the idea behind the Wilcoxon RankSum test. So how do we determine how high is high, how low is low? Okay, our test statistic is T1. This is the sum of ranks for population 1. This is the sum of ranks for population 2, T2. We just look at T1, okay, and we subtract off what we would expect to see from T1, the expected sum of ranks if these two populations are equal to each other. That's N1 times N2 plus N1 times N1 plus 1 all over 2. That's in the numerator. And in the denominator, we have the square root of N1, N2 times N1 plus N2 plus 1 all over 12. Okay? So how different is the actual sum of ranks for population 1 from what we would expect if those two populations were the same in the standard deviation units if those two populations are the same? Okay? So how different is this thing? How different is our sample evidence from our hypothesized situation? Our hypothesized situation in standard deviation units. Okay? This is a z-score. We can compare it to a z-axis, use the p-value approach, the critical value approach, just the same as always to draw conclusions about this set of hypotheses.